Okay, so we're still on the subject of triple integrals because that's what this section is all about. But now, what we're going to be doing is integrating it over more general regions. So not a box, basically. So let's say we have, what we're going to have is something like this surface up here, okay? So we have a top, like, flying carpet thing. And then we're going to have a lower one, too. So something down here, like that. You see that? So there's a higher one and a lower one. So this will be z1 of x comma y. And this will be z2. Well, actually, I'll make the top one 2 and the bottom one 1. Just because that's usually the conventional way to label them. Okay, so z2 is always going to be above z1. And functions of x and y are going to determine surfaces in 3D space, right? So what we're going to be doing here is we have these two surfaces, and then let's say we're integrating, the region, W, is determined by z staying within, between these two surfaces, okay? So here's what the bounds are going to look like. Something like this. And it is, I'll write up the notation and then I'll explain what it means. So this means with our xy's, so with our points down here, with our xy's, things on the xy plane, within D. This means within or included in. Something like that. Okay, where D is the projection onto the xy plane. So what that means, that fancy saying, so what we're going to have is basically z, the height has to stay between these two surfaces. It can't go above z2 and it can't go below z1. Alright, so it has to be in between these, and we have some predetermined d. They'll tell us in the question what it is, or we'll have to figure it out given what we're given. So this is D down here. They'll give us that in the question, or we'll at least be able to figure it out in some way. So what you'll do is basically take D. The concept behind this is that we're drawing straight lines up, right, until we hit the very top carpet. So then we'll get some surface up here, and it'll intersect at some surface here as well. Okay, so this D down here, that's just a reference point. And our volume, W, our region, is actually this thing. I'll shade it in right here. It's just this. This is kind of like blob floating in air. And what D is called, the domain is called, and here you might have seen this in Math 32A as well, if you've taken that course. It's called the projection onto XY plane. Okay, and the way I like to think of a projection is, let's say you have a light up here. I didn't leave myself enough room. Let's say you have a light coming down, right? A little light, and this is the shadow that it casts. The light would be more up, way above this screen to get a straight down. But anyways, so this is the shadow that it casts. So basically what we have, this is how you would write it as a triple integral. So we have, this is the general way of writing it, right? So then we have something like this. Okay, so that's the very general formula. And then, given what we know here, we can write it as, and we don't know any specifics about D, because I didn't give you any. I'm just talking generally right now. The problems will give you specific details about D, but now this is the way we can write it. So we have the bounds on Z. Z is going to be our inner integral here. And then f of x comma y comma z dz. And then we have either dx dy or dy dx. And this outside can be just considered dA. Okay. Okay, so if this looks confusing, it probably is. But basically what this is saying is that we have our double integral on the outside, right? Like let's say you just erase everything, you get rid of everything in parentheses, then we're left with something that just deals with dx and dy, right? But now that we're dealing with a third independent variable, z, then we have something that we have to kind of like squish in the middle here. So this is kind of like an insertion here. But in this case, as opposed to the other simpler case of integrating over a box where all of the bounds were constants and z was bounded by constants as well, now z is bounded by functions depending on x and y. Okay, so that's the big crucial difference here. So z is bounded by functions dependent on x and y. Okay, so essentially what this means, this is a very important connection here, a really crucial statement, because what that means is that our z1 of x and y and our z2 of x and y, they're both surfaces, right, in 3D space, but they both depend on xy points, like where we are on the xy plane. So basically, everything that's going on in this solid depends on what's going on in the xy plane. So that's why this outside part is very important as well. Okay, so the inside is kind of, I mean, all three variables are related in some way, but anyways, this is very important, the connection between z being determined by x and y. Okay, all right. So then, as we did with double integrals, with triple integrals, there is a special case, of course, because there's always a special case for something or other. So this is when our f of x, y, z equals 1. So when f of x, y, z equals 1. So this is kind of like, remember, okay, I'm going to do a little throwback here to double integrals. When we had double integral over d of 1 dA, this was equal numerically to the area of the domain, right? And we said this is still technically a measure of the volume, but numerically, like let's say your area, the area of your domain was 4, then your volume would be 4, okay? So in this case, in the three-dimensional case, then what we would have here is actually that this would equal, okay, I'll just draw arrows here. So this triple integral, when f of x, y, z equals 1, this is going to be numerically equal, so numerically equal to volume of W, of your region W. And this is a three-dimensional thing, or object, right? Okay, so yeah, that was just an important case that I wanted to note. If they ever ask you for the volume of something in a question, like find the volume of blah region W, then you would automatically have to know that, make the connection that your f of x, y, z could equal 1, which actually simplifies things a lot, because 1 is, like I said before, 1's a pretty nice number. So is 0. If you had 0, that would be amazing. But anyways, so yeah, it's important to make this connection that if your f of x, y, z is 1, then your answer is going to be equal to the volume of W. Okay? All right. So now for one last example.